So let's define a curve. Let M denote a differential manifold of class C to the K, with K at least 1. And I denote an interval of the real line a curve is a map gamma from I to M of class C to the K. What does that mean? So let U phi denote a chart, which means an open set with coordinates, and P, a point of the interval I, that's mapped in U, such that gamma of P is a point of U. So that means you have certain U, you have a certain I, which is an interval of the real line, you have a certain P in I. Gamma will map, so the curve gamma will map the interval onto some curve, which is in red, and the map of the image of P, gamma of P, we want to fall inside this U, this open set. Now this open set has some coordinates because it is an open set of a chart. So how do you express the curve? By means of those coordinates. There is a neighborhood I prime of P that is mapped in U, which means that if you restrict to some neighborhood here, you will get the portion there. Maybe we can use some other color. So this is I, and in green we have what we call I prime, and I prime will be the portion of the curve that falls inside U. So what we can say about this, that we can restrict our curve to I prime. I use the same symbol gamma for the restriction because I don't want to burden the notation. So gamma now can be seen as a curve which maps I prime onto U, in U. And of course we have phi, which was part of the definition of chart, and that is a diffeomorphism U to Rn. And so we can build the composition phi composed with gamma is what? Gamma takes you from I prime to gamma of I prime, which is inside U, and phi takes you from gamma of I prime to Rn. So here you have coordinates of Rn, and here you have a certain coordinate t belonging to R. So once you compose the two, you can describe your curve as x1 of t, xn of t. That is a curve, your curve. Now it's described as a map from some coordinate t to n coordinates, x1, xn. And since by definition it had to be of class ck, that means that these functions are k times differentiables for every I. Is a k times differentiable function for every I and every chart, actually. That is a k differentiable, a curve of class ck. We want to define the tangent vector to k, to gamma. In the point P, let's assume that P could be t equals 0, but we don't need to be so precise now. Say the tangent vector to gamma in P is the derivative, the vector obtained computing the derivatives with respect to P and to T and calculating them in P. So I put P as the argument. This is a bit shortcut notation, but I think it's clear. This is a vector of Rn. And components. we say that two curves are tangent to each other. So two curves, gamma, which we now denote with x1 of t, xn of t, gamma prime, which we write as y1 of t, yn of t, are tangent to each other. In P, if they have the same tangent vector in P. So let's make a note here to stress that x and y refer to the same coordinate system, the same chart. They are not different coordinates for the same thing. They are different things with the same set of coordinates because they are different curves, but they refer to the same chart. Same chart if you want. So the two curves are tangent to each other if they have the same tangent vector. As you can imagine, what does that mean? It means that you will have your set, how did we draw it earlier, like this. So you have a curve gamma and a curve gamma prime. Totally different curves, but they may have the same tangent in P. This property does not depend on the coordinates. So we used explicit coordinates to define curves that are tangent to each other, but now we can show that this is an interesting exercise if you want, that this property of being tangent to each other is not dependent on the coordinates. So let's say we have yes, probably it's necessary to use a different notation now, not to make confusion. So instead of calling the two curves gamma and gamma prime, I call them gamma 1 and gamma 2. So it's early enough to change the notation. Okay, gamma 1 and gamma 2. Instead, I call gamma 1 prime and gamma 2 prime the same two curves in the new coordinates. So I use prime as the notation to emphasize the new coordinate system. So let's say that we have phi composed with gamma 1. Let's recall this was the first curve in the first coordinate system, x1 of t, xn of t. Phi composed with gamma 2 is the second curve, but in the first coordinate system. And we know that they are tangent in the first coordinate system. So using u coordinates. Then take another chart. Which we denote by the pair u prime phi prime. And you assume that P belongs also belongs to U prime. Otherwise, I have to take U prime with some intersection, and that intersection with U, and that intersection should contain P. Then you have a different parameterization for the two curves, which will be easy to write because it's sufficient to put primes here. So we put primes. This is phi prime, x prime, using u prime coordinates. By the way, the u prime coordinates are those given by the homomorphism phi prime, while the u coordinates are given by the homomorphism, diffeomorphism now, because we're assuming that there is a certain differentiability. But the map phi in itself is not differentiable. It's only when it's composed with another, the inverse of another phi, that it becomes differentiable. So you cannot say the phi itself is a differentiable map, because it doesn't make any sense. So what we want to show is that the property of being tangent doesn't depend on the coordinates. So we want to show that xi dot p equal y yi dot p implies x prime dot I p is equal to y dot prime I p. And how do you do that? Now there certainly is, so if we want to go back to our picture, we can maybe show our u prime. So you see there is certainly a neighborhood of P that belongs to both u and u prime. That's why we are working with open sets. Let me call it UP. So there exists UP, neighborhood of P, that is contained both in U and U prime. So there we can use both coordinates. That's where we can have both coordinates, and so we can compose the maps to go from one to the other. There we can use both coordinate systems. And in particular, what can we do? Phi prime composed with gamma 1. Let's consider the first curve in the second coordinates, phi prime composed with gamma 1. That we can write also as phi prime composed with phi to the minus 1 composed with phi composed with gamma 1. This is the change of coordinates and this is the first curve in the first coordinate system. First curve in the first coordinate system. This is the first curve in the second coordinate system. So let's recall that this was what? x1 of t, xn of t. This is a change of coordinates, so it goes from the coordinate x prime of x, let's say, and this is x prime 1 of t, xn prime of t. So basically we are just writing, we are viewing the first curve written in the second coordinates as this composition. x1 of x, x prime of x, and then x is an x of t. Yes. Let me not write equal here, because there's a change of notation, but this is what we do with a map. And therefore, if you want to compute a tangent in the second coordinate system, dt, and then you compute it in P, because we are interested in the tangent in some point, the point P, you can compute it as the derivative of the, using the Leibniz rule of the composed functions. So you have dxi over d prime xj dxj dt. And that has to be calculated in P. So we want to show that two curves which have the same tangent in one coordinate system have the same tangent in the other coordinate system. We are almost there. We are taking the long tour because we want to establish some notation for the rest of the course. So it's useful to do it. So we can repeat everything for gamma 2. And for gamma 2, we have to use y coordinates. We call them y instead of x. So what we get is dy prime, dyi prime over dt, p, that's equal to dyi prime, dyj, dyj, derivative dyj respect to t in P. Okay, so now let's take the difference of these two equations. And we have dxi prime over dt in P. So the tangent to the first curve in the second coordinate system minus the tangent to the second curve in the second coordinate system, that is equal to the difference, so we copy the difference. P, by this I mean that everything has to be computed in P. So let's be precise there, minus dy I prime divided by dy yj P dyj over dt P. Now, we want to show that, let's recall what we want to show, that if they are tangent in the first coordinate system, they are tangent in the second coordinate system. Being tangent in the first coordinate system, means that these two are equal by assumption. In P. And what we want to show, that these are equal. That this difference is 0. We want to show that this difference is 0. So to show that this difference is 0, it is sufficient to show that the Jacobian here and the Jacobian there should be equal. but these are equal, because as I stressed before, these are x and y are just different names, but in the same coordinate system. They are different names because we are calculating them in different points, because the curves cover different points, but now we are calculating them in the same point. So it doesn't really matter whether we call them x or y, because this is the Jacobian of that relates the same two coordinate systems calculated now in the same point. So this is what I stressed before. So x and y refer to the same coordinate system, but we could use different names simply because the curves cover different points. They go through different points, but they go through the same point in P. That's the only thing that matters here. They have one point in common, and now we want to show that they have the same tangent there. But they have the same tangent there because these are indeed equal, because they are equal, because you can say they are the Jacobian for the change of coordinates between phi prime and phi, which know nothing about the curves. So we said previously that this change of coordinates here doesn't know anything about the curves. It's phi prime, yes, phi prime composed phi minus 1. Let me write it this way. All right. So we have a meaningful definition of curves that are tangent to each other through the same point P, and this allows you to define an equivalence relation. Between curves. Or among curves, because there are more than one form, curves through the same point P. And we say that gamma is equivalent to gamma prime. Let's say gamma 1 is equivalent to gamma 2. If they have the same tangent in P. If they are tangent to each other in P. And then we can consider the quotient between the set of all curves through P and this equivalence relation. That is called tangent space. Space tangent to the manifold in P. So the quotient between the set omega p of all curves through P and the equivalence relation just defined is called tangent space to the manifold M in P and denoted by TP, or you can find also Tm comma P. So, in other words, if we consider a V belonging to Tp, that is to say, an equivalence class of curves through P. And associated with the vector that is tangent to P, which is common to all the representatives of the equivalence class. So with the vector x1 dot P xn dot P, which is a vector over n, common to all representatives of the equivalence class and independent of the coordinates we use. coordinates and chart we use. Then we obtain an isomorphism between Tp and Rn. An isomorphism between Tp and Rn that endows Tp with a structure of vector space, which endows Tp with a structure of vector space. So all this is to be sure that whenever we use specific coordinates for the tangent, we are actually writing something that does not depend on the coordinates, and so we can refer to the tangent vector as that one written in those coordinates, although its definition is of course more abstract, since the definition should not depend itself on the coordinates we use. So that's all for today, and the next lecture will be tomorrow at 9.